Well, thanks for having me. I really appreciate it. There's been some really fabulous talks in all the tracks today, so I'm really honored to be here. If we haven't met, my name is Leslie Carhart. I'm a digital forensics and incident response professional. I've been doing that for about 14 years now, working in computers well over 20. I work for a company called Dragos, and we do specifically industrial control system and critical infrastructure security. I do a lot of shouting about people and in the news and in Twitter and on my blog and stuff. If you haven't seen me there, I'm probably saving you from some grief. I also teach martial arts and marksmanship to kids. And I am, well, former and current Air Force. I'm a reservist now at like about 19 and a little more than a half years. So I'm kind of excited about that. That's kind of cool for me. Yeah, and I'm going to talk to you today about industrial control systems and how to secure them and why that's important. And it's a really important topic to me because I'm involved in incident response on all kinds of critical infrastructure systems, from power to water to manufacturing and transportation. And I see how close we come to things getting really, really bad because of cybersecurity deficiencies and process deficiencies that allow us to fail in securing systems properly because things aren't communicated properly and people don't build the right programs for industrial control systems. So well, we're going to spend a little time talking about what I've seen work and not work and why I need you to be a part of this process. So I would imagine a lot of you, whether you're working for government organizations or working for corporations, big, small, municipal, probably have some industrial control systems in your environment. Now, they might be as simple as data center control systems, building automation controls, cooling systems if you work somewhere where it gets warm in your data center, et cetera, backup generation systems. And those are all very, very important processes in your environment. They keep things running, they keep catastrophic events from happening in your environment. And they do really important things, even if we don't notice they're gone until they break. And in many cases, you might not be consciously aware of those systems. And in other cases, you might know they're there, but you kind of just expect them to keep working or somebody else to take care of them because they're maintained by a vendor. So you're kind of ignoring them from a security context. And you might have been instructed in a lot of cases to keep them secure without any direction whatsoever and had little success at that. And certainly if you're trying to secure them and you're actively working on a program to do it, I can imagine some roadblocks that you're facing because I face them helping organizations, working in companies, working in organizations of various types, municipal, et cetera. And it's tough. Securing industrial control systems is a challenge. It's very different than securing our IT networks, the things that we're more familiar with. So why is this so important? Why am I talking to you about these systems in specific? Well, the risks and the threats that are posed against those systems are increasing. And that's for a lot of different reasons. First of all, our industrial control systems, all the way from building automation to sophisticated power systems that do our power generation and transmission across the world, are increasingly connected to networks and also to the internet, directly or indirectly. And that has huge implications, of course, because there's more access to them. It doesn't require a person walking into a building anymore. And a lot of the devices and protocols that are out there and are out there long term, and we'll talk about that, those long life cycles of industrial devices, a lot of them were never intended to work on the internet or work on networks or work over TCP/IP. Some really common protocols like Modbus were invented in the 70s. And obviously the internet was not a thought on people's mind at the time. It was making the lights go on and off, things like that. So industrial control systems have been around for a very, very long time because they're not necessarily just digital computer systems. They're also analog systems and mechanical systems. You can have a grain mill that's powered by water that has gears and pulleys, and it's doing industrial processes. It's controlling an industrial process. So it's ostensibly an industrial control system. So industrial control systems, particularly electronic and analog ones that weren't originally networked, have been around for a very long time. And that doesn't mean that they were intended to be networked via networks that are familiar to us today. Maybe they were intended to be connected via serial connections or coaxial connections, not are more familiar, Ethernet standards. And the creators of those protocols didn't really think about the things that could go catastrophically wrong when they were connected to a public-facing network. Yeah, somebody commented in the chat, building automation systems are not simple. No, they are not. They're actually very complex, and they do a lot of things in modern buildings. We'll talk about that a little bit more. ICS devices must also often remain insecure for various logistical and technical reasons. We're going to talk a little bit more about that, but everything from vendor specifications and warranty requirements to the long lives that they live to compatibility between the various parts of the industrial systems that are purchased as a package. So there's a lot of reasons why individual devices in those environments have to remain insecure, and there's nothing we can do about that from a cybersecurity perspective. We have to think of mitigations outside of those devices themselves. And even more overarching, industrial control systems run everything in our lives. If you turned on the water today and you don't have your own well, well, you could even technically consider your own pump an industrial control system. But if you turned on the electricity today, if you flushed a toilet and used a sewage system, if you ordered a package that came through a logistics system that had scanning and processing of packages like Amazon, that's all industrial control systems. Our society functions on them. We live in a just-in-time economy now where things are produced as they're needed and shipped as they're needed, and everything in our society runs on industrial control, down to our own buildings, the lights, the water, the temperature, the elevators, all the things in our corporate and our governmental buildings as well. And unfortunately, bad people know that too. They know that our society is dependent on these industrial devices and that they're connected to the internet and or connected to networks that are connected to the internet. And so that makes them a very, very desirable target for adversaries. And we really need dedicated security programs for industrial control systems and infrastructure environments. And that means not despite them, so trying to ignore that they exist, or pretending that they're not a part of our security program, or that they're a hurdle to our security program. And we need to build those programs without false assumptions about what we can and can't do in cybersecurity in those environments. And we can't try to fit them into an IT cybersecurity box. It just doesn't work. The devices, the needs, the organizations, the culture, the vocabulary, everything is too different. We have to, although we can build our OT program into our IT program, and they can share resources, they can share people, they can share knowledge, there needs to be separate elements of both of those programs. And I'll talk about what some of those documents and elements are that need to be distinct and discrete in your industrial environment. Now, most of the audience here today is retired military, veterans, Guard and Reserve. And we have a great advantage coming into industrial control system cybersecurity. You are some of the best candidates to build these bridges and build these programs that we need so badly in industrial control systems. First of all, because in the military, we are taught right from the bat, right from basic training to manage and measure risk. We understand our OODA loops, we understand how to make decisions quickly that involve risk and threat and consequences. And that is super crucial in industrial systems because we're dealing with things that are kinetic. We're dealing with systems that impact people's lives, safety, health, things that can cause fires, things that can cause injury, loss of life, contamination of the environment, catastrophic system failures that are very costly. Yeah, so everybody's happy I said OODA loops in my talk. I love this audience. Okay. Yeah, but I mean, you're good at measuring those things on the fly, and we have to be in industrial control systems because things can go catastrophically south really, really fast. When you're talking about, say, a smelter that's dealing with molten metal, or a power system that's dealing with massive quantities of electricity. When something goes wrong there, you have to make decisions like that, and they have to be based in not just cybersecurity knowledge, but in knowledge of the process, knowledge of risk, good calculated risk decisions, the threats that you're facing and the potential consequences. You also understand how to go into environments where PPE is a requirement, and that's a big part of my job, is going to bizarre places, you know, extreme environments, environments with major safety concerns where I have to have the right PPE, I have to have the right safety training, And that requires a certain mentality as well, to be aware of risk and aware of what it takes to mitigate risk, and be responsive to people telling you when you have to make changes to your behavior or do something rapidly because there's a problem. And we understand mission. We understand mission statements. We understand that organizations have various missions in various parts of the organization. And that's very, very true in industrial environments. Our mission as cybersecurity people is not the same as the mission of the industrial process people who we're going to talk about. We have different missions, and that's okay. They can be tied together, and they should be tied together, but we have to understand their missions and their objectives, their strategy, because that's going to impact how we do good security for them. And we certainly, in many roles in the military, have had experience dealing with non-standard computer systems, things like avionics, vehicle maintenance, civil engineering, et cetera. So we have a lot of exposure to things that don't look like normal IT computers when we're deployed, et cetera. So we really need your people. We really need all of you in industrial control system security, because there's such a shortage of people in that field, or who want to learn that field right now. All right, so let me give you a little primer and some vocabulary, because I said vocabulary is a problem here. We're not always using the same terminology as the people who work in industrial environments, and that can cause some angst and anxiety and miscommunications. So first of all, there's a term OT, or operational technology. That's a term that was actually coined by IT people to differentiate themselves from industrial environments, but we use it. It's an overarching term that refers to like process technology and the environments that have industrial technology in them. You don't necessarily have industrial control systems in every OT environment. OT is kind of like a general overarching term for process type things. So we use that term to usually like describe an OT environment, somewhere where those systems might exist. But more specifically, industrial control systems. I mentioned earlier that they don't have to be computer-based. A lot of people use SCADA and ICS interchangeably, and they are not the same thing. A SCADA system is part of an industrial control system, absolutely. But not every industrial control system contains SCADA by far, by massive percentiles. SCADA is a type of control system that controls multiple parts of a process. We'll talk about processes and process loops. It coordinates them, and it does advanced data analytics, things like that, for large scale operations. But there's plenty of industrial control systems in the world that are analog, that are a simple PLC, single computing device, and they don't involve SCADA at all. So industrial control system can be any of those analog, mechanical, or digital things that control part of a process. When we talk about an operator, we're talking about the technician who uses the industrial control system. They make the widgets on the factory line. They make sure that the power generation is working properly in the power plant, et cetera. When I talk about an engineer, and these are not like cut and dried terms, but they're pretty standard in various verticals. An engineer is usually the person who makes the system go. So repairs it when there's a problem, monitors its function, configures it, updates it, et cetera. Again, these are not universal terms. Every industrial vertical is different, but yeah, so this is kind of a common terminology that you'll see a lot in these environments. So if you want to know about how the system's updated, probably go to the engineer. If you want to know what can go catastrophically wrong, either the engineer or the operator can probably tell you that. You know, there's usually a lot more operators than there are engineers. So what is this process thing that I'm talking about? So I'm talking about processes. A process is a series of discrete operations, so things happening, mechanical, digital, analog, whatever, that accomplish a physical task. So something kinetic happens. And there is a billion different processes. We've talked about some already. So they could be hydrocracking oil or electrical generation. They could be making cans of tuna and labeling them on the assembly line, or pumping well water, or packaging goods and shipping them off into trucks. Yes, big tuna is my favorite example of industrial process. I don't know why, I just like the idea of the tuna cans getting filled with tuna. It's very exciting. And we're going to talk about processes, and we'll talk about some that I like as examples. But keep in mind that processes can be component parts of other processes. So if you've got a complicated process like a manufacturing assembly line, you're going to have lots of little processes that go into a big process. And that's where things like SCADA might come in, when those all have to be coordinated. So a process loop, all processes can be broken down into, well, industrial processes can kind of be broken down into a process loop. So this is what an industrial process typically looks like, especially if it involves like ICS. So you have some kind of actuator, which is your motor or your valve control or your pressure valve, things like that. You know, something that does something mechanical or temperature related. It has a kinetic impact. And then you need to make decisions about what that's going to do, right? So you have a controller that tells it when to go on and off. Now in a simple mechanical device, that might be it. Typically in those loops, there's some kind of sensor, and it doesn't have to be a digital sensor. It could be analog. It could be a pressure release valve that hits enough pressure and it opens. So it's detecting that there's a pressure condition, but it's just a mechanical device. But you have some kind of sensor that helps the controller make a decision about what to do next. So in a digital system, the controller might be something like a PLC, a simple computer. The actuator could be like motor controller or a valve release or something. And the sensor could be anything. It could be a temperature sensor, it could be a pressure sensor, motion sensor, etc. So, and these work together, obviously, to make something happen. Let's look at an example of that. So back in the before time when we could all like go outside and go travel and go to buildings and conferences and things, we all saw this thing. I know it's been a while, but try to go back to the before time with me. This is a revolving door. They have them at buildings sometimes. You walk into it, it's motion sensing, and when you stand in the door turns, and then when you get out of the door stops turning. Yes, hopefully something that's still familiar to all of us in 2020. All right, so what is this door doing? It's doing a lot of stuff, actually. It's a pretty fancy control loop. So there's a sensor in it, right? It has to know if you're in the door or not. So there's usually like a motion sensor in it. But it doesn't just sense if you're in the door, it also does things like sense obstruction. So if the door is jammed up or there's something going wrong with it, it stops trying to turn. So it doesn't break itself or break you. So you've been in that door and you've gotten too close to the door and it's just stopped turning. Well, that's also a sensor in that door. And then of course you have an actuator because you've got a motor that makes the door spin around, yeah? And then you've got a controller that's making decisions based on those things about when the door should be turning. So is there somebody in the door? Okay, my logic says if there's somebody in the door, I'll check if the door is obstructed. Well, the door isn't obstructed, so I can start turning. And is the motor turning already? It has to check with the motor, the actuator. Hey, is the motor already turning? No, it isn't. Okay, well, my programming says in this very simple computer, now I make the actuator go. Now I make the door turn. And I keep doing that check in sequentially, like every few seconds. And I say, okay, is there somebody in the door? Is it obstructed? Is the motor turning? Is it not turning? And the controller has simple logic programmed into it that tells it what to do in each one of those conditions. So that's a very, very simple process loop. There are only four things. This is a military standard for this, and I really like it. It's the functional mission analysis perspective on process loops. There are only four things that can go wrong in a process loop, okay? So think about our example of the door here. Actuator fails to start when it's supposed to. So that means you get in the door, and what happens? Well, it doesn't turn. Yeah, the actuator doesn't start. The door doesn't start turning. Not too big of a deal. You're kind of annoyed, but okay. Actuator fails to stop when it's supposed to. Well, I mean, if you're out of the door, that's okay. It just starts spinning forever. If you're in the door, that could be rather uncomfortable. If you're obstructing it and it hits you in the face, yeah, that kind of stink. Actuator starts too early or too late, so the timing's a little bit off. So you get in the door and it hangs for a second, or it smacks you in the face. Not very good. Actuator goes on for the wrong period of time. So again, it's either, in the case of the door, this is pretty simple. It's either a case of the door spins for a really long time after you get out, or it smacks you in the face when it's obstructed. So not too deadly consequences in our little revolving door, but you can think about more complex processes, like things like a smelter, and how severe those consequences could be if the molten metal from the smelter starts pouring out and doesn't stop pouring out at the right time, things like that. These things can start becoming very catastrophic. A real industrial process, oh my gosh, though, it's really complex. It's usually a combination of many, many process loops that are all being coordinated. And they can be coordinated by a few different things. They could simply be managed by humans, or they could be controlled by a device like a distributed control system, which is kind of just one computer that kind of just times everything together in a facility, or something more sophisticated like a SCADA system. So it depends on the environment and the geographic spread of the facility and how many things are being controlled and what complexity. But yeah, usually you have some kind of master computer that's making decisions for all of the different control loops. Yeah, so that's kind of a general idea. And this is a small picture. In a real complex industrial process, take this image and times it by 100. There's tons of little control loops that are happening that make up the big process. Yeah, so somebody asked, so SCADA controls ICS? Yes, a SCADA system or a DCS make all these things work together. So they help the system coordinate its activities by giving feedback to the human operators and by coordinating control loops in preset ways and configurable ways. That's a simple explanation of what those things do. These computers all make decisions on their own. The controllers in each one of these control loops will keep doing the thing they've been programmed to do forever. If you program a PLC to do something, until the PLC goes out of power or breaks or something, it's going to keep making the actuator go when it's programmed to, when it gets the right sensor input. These control loops will independently function until something catastrophically fails, which could be a very, very long time. But to keep them coordinated and timed together, you need either a human brain or some kind of computer that's making sure that they're all on the same timing and they're all functioning together properly. All right. So yeah, so many devices in a real environment are going to work in synchronization. And that means that there's a lot of different protocols in use because you have to have a bunch of different industrial devices working together, maybe of different eras, different vendors, different functions. And in each vertical and each part of that vertical, there's different vendors in use and there's different protocols in use. So industrial control systems really can get very complex. In a lot of industrial control systems, we're dealing with 4 to 8 different protocols that are specific to industrial, as well as multiple vendors. There's a lot of things going on in those networks. And we draw that out using a model. Now, everybody gets angry about academic models in cybersecurity. People get mad about the OSI model. They get mad about the kill chain. They get mad about all the academic models. So this is another academic model. No academic model is perfect, okay? No academic model is ideal. It won't show you every circumstance, every possible eventuality. They're tools to help us learn about stuff, right? So Purdue University created this model for industrial systems, and it's not perfect. There's plenty of exceptions out there, but it gives you an idea of what they kind of look like. So I like it. It's just a tool to kind of understand what's going on. So what they did is they broke industrial environments out into levels. And at the tippy top of this, there's a corporate network. So that's your company or your organization, your normal IT-based network where you have your email and your internet access and you watch Netflix, whatever you do all day. And then usually, because I'll tell you later why air gaps are a lie, you have some kind of DMZ to get into your industrial environment. So firewall, VPN, whatever, some kind of DMZ to get into this separate network. Beneath that, you have an operations network where you have like, you're controlling PCs, things that look kind of familiar. Your PCs that you do updates of your system and programming of your system with, your reporting systems, analysis and support systems. So things that look pretty familiar from an IT perspective. Beneath that, we start having more like embedded type systems. So like the displays that show us the status of our systems, our human machine interfaces, or our alerting and alarm systems, things like that. So more like embedded XP kind of type systems, maybe some Linux systems. And then beneath that, we start getting into our very simple analog devices and computers. So things like PLCs and RTUs that are very simple computers. And they're doing those types of operations part of the control loop. So they're making those simple programming decisions about what's going to happen to our actuators. And And at the very, very lowest level, we have very simple devices that just do things like provide sensor data or instrumentation data. Very, very simple devices at the lowest level. Very often just simple electronic devices that provide analog type inputs or very simple digital inputs to those other devices. So again, we've gotten from the familiar to the very unfamiliar at the bottom of the Purdue model. But between each one of those levels, we have different protocols, different transmission methods. Your connections from 0 to 1 might be serial, to 1 to 2 might be Ethernet, to 2 to 3 might be more familiar IT type protocols like SMB and various TCP/IP type stuff. So all the way up to your DMZ, where you see familiar things like VPN and RDP, things like that. So lots and lots of different protocols at use, but it helps to kind of think of it as this layer cake of devices, because all these things make up an industrial network. Now, this isn't always accurate. You don't always have a good DMZ. Sometimes things are a flat network. Sometimes they're very porous DMZs. Sometimes there's a modem plugged into level 2 that allows the vendor to get into the network and break segmentation completely. But it's a model, it's helpful, it's something to study. So you need to evaluate if industrial control systems exist in your environment. It's really easy to know if they do if you work in like a critical infrastructure industry, like power, water, gas, municipal services, etc. They certainly exist in manufacturing environments. So if you have manufacturing in your organization, you're going to have some industrial control devices to be concerned about, as well as any organization that does like bulk logistics. So tagging, scanning, processing of devices for shipping, things like that. A lot of that is industrial control systems. And at almost every organization, there's some building automation controls. So if you are somewhere where it gets very hot, you probably have some cooling systems. If you work somewhere that it gets very cold, you probably have some heating systems. You probably have some backup power systems, fire suppression, things that are very critical to your operations. If your data center catches on fire or overheats, what goes down in your environment? How bad is that? Is that as bad as somebody infecting the entire network with ransomware? In a lot of cases, I bet it is. So you should be thinking about those systems. You should be doing some very careful introspection to see if you have industrial systems in your network. If you do you think about them? Do you think about their security and what their security actually means? So they often exist on separate subnets or VLANs. You might not see them in your security monitoring appliance. They are very, very rarely air-gapped at all, but they're also often not monitored because of that, because they're on various subnets and VLANs that you don't have your monitoring appliance on. They often perform important tasks that are not considered in your risk modeling. Again, what happens if your data center overheats? Where does it go? Where's your redundancy? What happens? How long are you down? How long does it take you to restore those systems? What happens if it catches on fire and the fire suppression system doesn't go off? What happens if all your backup generator systems don't work, et cetera, et cetera. We often consider the systems too sensitive to do any security assessment on, which is a very bad assumption to make because we do have to know what their security posture is. I'll talk about some tactics for that. There's unfamiliar protocols and we don't know how to deal with them. We don't always have dissectors for them. So we don't know how to deal with those industrial protocols or how to monitor for errors or security problems on them. There's unfamiliar devices. Like, of course, we're nervous about poking at PLCs or RTUs when we don't know what they do. And there's generally, very often, a very unhealthy culture between the ICS staff and the cybersecurity staff due to us having a bad approach in the past to auditing them and telling them to do things that are impossible. So that's a big problem. So here's my top 7 misconceptions about ICS security that I want you all to know. So first of all, ICS is an edge case. It's not an edge case. Industrial devices are all over in your environment. If nothing else, they are all over in your building automation, your power backup, and your fire suppression systems, things like that. They are all over your environment and they do important things to your business. The second misconception that I deal with a lot is that it has to be out of scope for scans, pen tests, and assessment. No, there's very, very specific requirements for how you can do those things. And I'll talk about some ways you can do them. You can't just go out there willy-nilly and just start scanning things because you very, very likely can break an industrial device. They're very simple computers. It's not that they're fragile. It's just that they don't have like things like fully implemented TCP/IP stacks on them. So they don't know how to handle like half of a connection, things like that. So you can definitely freeze them up or break them by trying to vulnerability scan them or assess them. But we have options there. That they're arcane and require specialized training to learn. I just went through the Purdue model. At the top of that Purdue model, a bunch of those systems look really familiar to us. They're mostly Windows-based. They're things that we know how to do security on, forensics on, stuff like that. And even if we can't do detailed analysis of those lower level systems, we can still look at the higher level systems and do a lot of security there. That those systems are protected by air gapping, data diodes, or segmentation. I've seen one network in the last year in my professional role as a ICS security person with data diodes deployed. Almost nobody's spending the money on them. Air gapping is a lie. It's just a total lie. People who say that they are always have to bring in data and get data out somehow. It's usually a leaky firewall, DMZ. Yeah, so air gapping is just an absolute lie outside of the very most secure government type environments. And segmentation. Segmentation is only as good as the DMZ between the segments, or the routing between the segments. And in industrial environments that aren't monitored well, usually firewalls kind of get rules tacked on and tacked on and tacked on, exceptions, and they get really Swiss cheese and leaky. That it's purposely neglected for security updates and stuff. No, there are very valid reasons why we can't update industrial control systems. A lot of it has to do with how those systems are deployed and how the various devices across the Purdue model integrate with one another. And they're also very long life cycle systems, so they're meant to stay in production for 20 or 30 years. That they could be easily secured using modern security tools. No, you have fun putting EDR in a Windows 95 computer with 16 megs of RAM. No, we have to take other approaches to doing security on a lot of them because they won't support modern security tools for various reasons. That doesn't mean that we can't do security. It means that we need to be creative and adaptable about it. And that they're vulnerable simply because individual devices are insecure. I see a lot of security people go nuts because they find a vulnerable industrial device on Shodan. A single device being vulnerable doesn't necessarily mean a lot to that big complex process of processes. You have a bunch of safety controls there, overflow valves, pressure release valves, physical controls, human controls, things preventing catastrophes from happening. So a single device being vulnerable doesn't necessarily mean the process is vulnerable. So real talk, here's the reality of the situation. Industrial cyber attacks are on the rise. Industrial control systems are often based around legacy hardware protocols. Yes, that's true. They have to exist for a long time. Familiar IT technology is becoming more common. Yes, IT and OT are converging, absolutely. TCP/IP is increasingly common in industrial environments, abso-freaking-lutely. Air gapping is in fact a lie. You will almost never see air gapping in place in an industrial environment, even if they say it's air gapped. Just assume it's a lie. ICS protocols rarely have authentication or encryption. Yes, that's true. Their job is to work. Their job is to make the power go and the door to turn and the tuna cans to get filled with tuna. It is not to do security. Yeah, there's risk management decisions made there, very smart risk management decisions about people will die if this process starts working incorrectly because of overhead from security stuff. ICS technology can be sensitive to scanning and exploitation. Yes, absolutely, because again, these aren't always fully featured IT devices that can handle scanning type things. They can't be banged on. They don't know how to handle it. But that doesn't mean that there aren't other ways to work around that to test that they're secure. Operators have different and usually correct priorities. They know about the consequences in their environment that can happen. They know about safety. They know about the risks to their process. They know what will make people die. They know what will make the process devices explode. Those are their priorities, and those are very important priorities that you should be listening to. ICS is comprehensible, and we need to learn it. Absolutely, this is a very important thing to understand to all of our environments. So first of all, why are IT and OT converging? Well, it's just because commercial off-the-shelf IT stuff is cheap and accessible. Why would we keep rewriting ways to send network data when we've got TCP/IP? When we can replace hardware components with things off the shelf when it breaks? It just makes sense. Building custom stuff, proprietary stuff, makes things harder to maintain, to repair, to make cost effective. It just makes sense to use more IT technologies in industrial environments all the time. Why network it? Why are we networking it all? Why are we connecting it to the internet? Well, because remote access is a big concern, especially in the age of COVID. People need to be able to access their industrial systems from afar. And that can often deal with like extreme weather environments, things like that. It's really important in a lot of cases for operators to be able to access things remotely. You don't want to have to climb to the top of the mountain to fix the power substation. Remote and centralized process control, so things like SCADA. If you want to do distributed control of your industrial processes, then they have to be able to talk to one another across potentially large distances. Historian and monitoring. So we have something called Historian in Industrial Devices that does monitoring for how the process is working, the efficiency, what's going wrong. Think of it kind of like SNMP for processes. So what's going wrong, what's working, what's down, what's up, things like that. So you get a lot of telemetry data and statistics that's important for our operators and engineers there. So that data is important to collect centrally. And system efficiency. Obviously, if you can coordinate things down to a microsecond or a nanosecond in your process, you can get a lot more efficient. So that type of remote telemetry and remote control data is very important to efficient modern processes. Now, why are air gaps a lie? Why don't we just air gap all of them? Well, first of all, air gapping is incredibly expensive because all of a sudden we can't do all the remote access we need to do. We have to send boots on the ground people to every site whenever anything needs to change or be monitored. Some connectivity is almost always required for process systems, whether it's to collect historian data, to make changes, do monitoring, etc. So you almost always need some type of telemetry or monitoring or remote administration capability. When people say air gapping, it usually isn't. Usually there's some exception they're not thinking about, whether it's laptops traversing, the transient laptops going from site to site, or some kind of firewall with very rigid exceptions, but there's still exceptions there, or the vendor who comes on site with a modem and plugs it into the system to do updates. So it's usually a lie. Data diodes, they're awesome. They're really, really cool technology. They only allow communication one way from a system. So for like getting monitoring data out, but they're expensive, they're confusing, they're hard to configure. So we hardly ever see them in place. And a lot of systems just don't support them. Why is everything legacy in ICS? Well, because these systems are purchased for long-term and they're purchased as a package. Think buying an IBM system in the 70s or 80s. You buy a power plant industrial control system, you buy all those levels of the Purdue model, from the very, very simple low-level devices to the normal IT Windows-based systems that are up higher. It's all warranted and designed to work together. You start pulling pieces out and replacing them, you either lose your warranty or your support contract, or things just start not quite working right. And in your power plant, things not quite working right can be very, very, very bad. Again, their concern is power working without somebody dying. That is a concern there. So just sticking a Windows 10 computer in there, if there's a slightly different protocol stack or driver, could cause a catastrophe. So normally people don't, the support contracts from the vendors usually allow only upgrades that the vendors have thoroughly vetted for a long time and they've evaluated, they've built, things like that. And if you touch it and you change it and something breaks, you're SOL. Maintenance windows in industrial systems are typically very rare, maybe once or twice a year. So everything needs to be arranged around those, and they're already very, very busy. So those are the only downtime windows. You can't just upgrade at 6 a.m. in most of those facilities. They're still doing things like generating power. So this requires that we adapt as cybersecurity professionals. We have to find other ways around that, and that's okay. So what's the threat? ICS cyber attacks are certainly on the rise, absolutely. Target attacks are very costly and they take preparation. So if you get infected with ransomware in your industrial environment or somebody just pokes at it, they can definitely break something, but it's going to be a very unpredictable impact. The adversaries that are trying to cause specific impacts to industrial devices, like causing the system to fail catastrophically or somebody to die, need to do a ton of research in advance of that specific system and build to understand what safety controls are in place and how all the bits of the process fit together and what versions of devices are in place and how they're exploitable. They have to know all those things from the process to the individual devices to cause a specific impact. So a very specific targeted attack against industrial devices is very costly. It takes time, it takes human resources, it takes intelligence in the systems, knowledge of cybersecurity, knowledge of processes. You have to have all those resources at your disposal. There are definitely groups that do have that knowledge, and what they've been doing recently is reconnaissance of lots and lots of industrial environments. They've been doing some testing that we've detected of various types of exploitation, especially on like small and out of the US, like non-industrialized nations, places where people don't report those types of attacks. They're using those types of facilities to test their attacks so that nobody notices. They're learning how those systems work. They're learning how to attack various systems, and they're building footholds in the IT and OT networks of various organizations so that if the right geopolitical conditions happen in the future, they will be able to rapidly launch an attack without the lead time of all this research and investigation. That's what we're seeing right now. Tons and tons of this reconnaissance and learning how to attack things in the future when the time is right. But yeah, like I mentioned, commodity malware and just general system tampering can have unforeseen impacts. It can have no impact. You could hit a bunch of buttons on an industrial control system and have the safety controls prevent anything from happening. But oftentimes things like ransomware will disrupt things at higher levels, like the engineering workstations and the HMIs, enough that the operators decide they can't see what's going on well enough with the lower level devices anymore. Now, like I said, the PLCs will keep doing their job forever, but at some point there's a safety decision made by the operators saying, I can't see what the levels are anymore, so we're just gonna safely shut everything down and wait for our systems to be repaired so that we know that it's safe to turn them back on. Yeah, and this type of reconnaissance that we're seeing from the advanced adversaries, it doesn't build security budgets. Nothing's exploded, so people are not getting more budgets or more security monitoring capability. But the reconnaissance and the foothold building is happening, and it's increasing. And by the time somebody actually decides to do something catastrophic, it'll be too late. So what should you know about your industrial control system to prevent these bad things from happening? So first of all, you need to know your overarching process. So how do things work? So not just from a computer perspective, but how are the widgets made? How does the power get generated? How does the oil get pulled out of the ground and made into something usable? You need to understand at a high level how those processes work, because you can't do any of this without that knowledge. You need to know your ICS network and system topology. So how is it laid out? How do the systems talk to one another? What does it look like in the Purdue model? And at each level there, what protocols exist? So how are the devices talking to one another? How do they do that? Is it secure, insecure? Is it something that you monitor with your network security appliances? Can you see it? Yeah, so lots of questions there. The limitations of those protocols. So if they're secure or insecure, whether they're plain text, you know, whether there's things you can monitor for them that would be in invalid states. Usually industrial protocols send simple codes to devices to do things, and there's codes that exist and codes that don't exist, or combinations of codes that don't exist. And if you see those things happening, you can make a decision that something's probably going wrong. Device make, model, and function. So again, the adversaries are going to want to know this too. So is it a vulnerable version of a device? Is it something that has some security functions? Does it not have any security functions? Are they turned on? Are they turned off? Yeah, so all those types of questions are very valid, and those are things that your engineers should know. Mechanical and physical and non-networked controls, specifically safety controls. What prevents the building from exploding if somebody hits a button on the HMI or changes code in the PLC? Are there controls that'll keep you safe? And what do those do? And what do the humans do? What do they monitor? What do they not monitor? And what can they see happening or not see happening? And interactions and dependencies between your various processes. What happens if your facility overheats because your HVAC goes offline? Does your process know about this, and does it shut down gracefully, or are they entirely disconnected? So things like that. Start here though. This sounds really complex. I've given you a lot of information today. Just start here. Identify the potential process environments you have to secure and go talk to people. I know this is a very difficult thing, but what you're going to do is you're going to get a box of donuts and you're going to carry it over to your industrial place once you go through the proper safety training and have your PPE. And you're going to sit down with your engineers and operators and you're going to give them a bunch of donuts, wearing your mask 6 feet distance right now, whatever. And you're going to have a good conversation with your operator and engineer staff. You're going to ask them about the process. You're going to ask them to teach you like you're a 5-year-old. You are going to be humble and let them teach, because people like to tell you about their job and why they do it well. And you're going to let them tell you about it all day because they like to talk. They like to talk about their processes. Most operators and engineers are very proud of what they do and what they maintain. So they'll want to tell you all about it if you're polite about it and you don't try to be a smartass. So shadow them, learn about the process, learn about how things function, and make it clear that you're not an auditor. You're not there to get them in trouble. You're not there to tell them to do things that are impossible, like update systems that can't be updated. Make them understand that you're a trusted partner. You want to work with them to help them do security better, but not to tell them to do things that are impossible. And you can only do that by learning from them. And you got to understand that you're never going to know everything about those processes. They are the experts, and they'll never know everything about cybersecurity, and that's okay. You're going to help each other build out the security better. And you've got to make that conversation work, understand that you have those different missions and priorities and vocabularies. Again, it's consequences, risk, and the process working properly first for them. Not what infection is happening, not that it's ransomware, not that this country attacked so-and-so. They don't care about that. They care about the place not setting on fire. So that's fine. Understand that. Operators care about consequences and risk. They care about things like loss of life, injury, contamination of the environment, process failures that damage the equipment or cost a bunch of money if it costs a lot of money to go out of production. And your findings in those environments in terms of security vulnerabilities or incidents may not result in any consequence or risk that they care about at all. So simply being infected with malware doesn't necessarily cause a bad consequence in an industrial environment, because it probably doesn't infect the PLCs. Those aren't Windows-based. Exposure of the system on the internet doesn't necessarily cause a consequence if somebody hitting buttons on Shodan doesn't do anything because there's safety controls in place. So you need to have that good understanding and dialogue about the process and key consequences. And you need to understand what can cause those consequences, what devices are your crown jewels, where you may have lapses in your mitigations, and you know, where you do have good mitigations, where you don't have to worry about security things happening. To learn more about industrial devices, pick a starting point. Industrial control system security is as big as cybersecurity is. So there's many verticals. Electrical generation cybersecurity is very different from oil and gas cybersecurity, and that's totally different from manufacturing cybersecurity. Different verticals, different technologies, different vendors, different protocols, that's fine. So pick the one that's applicable to you and start there. Just start with the vendors you have in use. Don't try to do everything in industrial cybersecurity at once. You can do a lot of OSINT to learn about those technologies for the things that your operators and engineers can't tell you. There's tons of manuals out there posted on Scribd. Look, don't poke on Shodan, just see how things are configured and what's out there, what versions they're running. Google hacking is great. You can find a lot of manuals and documentation on Google. And if all else fails, you can usually buy things like PLCs on eBay used. If you want to poke at them, buy one and poke at it, you know? Most importantly, learn about processes in your environment, learn about the consequences that can occur, and learn how your operations work. You've got to know that to do security well there. You cannot do security in a vacuum in industrial systems. Now, there's some formal training available through SANS, through my company, Dragos, through a lot of other organizations in the government like INL, through DHS. But it's limited in scope. It's not going to tell you about your specific environment. It's not going to tell you necessarily about your specific vertical. So understand that you are going to have to sit in that room or on a Zoom call and bribe your operators and engineers with donuts to help you out in understanding the systems. Absolutely, period. And what do you need to have to build a good cybersecurity program in those environments? So ultimately, what you're coming out of here, You need to have that good collaboration and communication between IT and OT. So fix that relationship. Fix that relationship so you can have regular conversations about cybersecurity. You need to understand the process, period, end of story. Auntie Leslie says you have to know the process at a high level. You have to understand the consequences of concern, end of story, to model risk, to figure out what devices you care about monitoring, what your crown jewels are. So what can cause those consequences? You need an asset inventory, period, end of story. Otherwise, when you have an incident, your incident responders are going to charge you hundreds of dollars an hour to make one. I've had to do that. It's very disheartening for me. And network maps. So your IT ones probably won't be applicable here. You need ones for your OT environment. You need an incident response plan for your OT environment. It cannot be a copy paste of your IT incident response plan. If it is, there's something wrong with your IT incident response plan, because your OT incident response plan is going to involve process shutdowns and contacting the facility manager and who you contact in operators and engineers in terms of various systems and potential consequences, crown jewels, etc. Those are all going to be in your OT incident response plan. It's a different environment with different concerns. You need to have a separate, at least section in your incident response plan for your OT environments. You need to have good crown jewel analysis. So once you know what systems are your crown jewels because they cause consequences of concern or they're integral to the process, you can start modeling risk down to those systems and looking at your mitigations, looking at the systems functionally to understand where things could go wrong and where you need to do extra security monitoring and management. Collection management. You need to know what data you have available to do monitoring and detect things that are going wrong. So what logs are available? Do you have packet captures? Do you have a network sensor? Do you have Snort or Suricata or a Zeek out there? Do you have logs that you can pull off the Windows host, and do you have access to those? So you need to have some type of collection management document that tells you what you have available for forensics and for network monitoring. And you need to understand regulatory requirements. There aren't too many in industrial networks, but if you have like NERC-CIP requirements, you need to know that because it's going to have massive impacts on your cybersecurity posture. So here's some easy fixes for y'all. I want to end with this. So your solutions for these problems that I've been talking about. So your number one fix for everything is good segmentation and DMZ control. So if you're thinking about the Purdue model having that DMZ between you and the OT environment, that DMZ, that firewall being strong, not full of holes, being well maintained and well monitored is really, really important. And not breaking segmentation with modems or with out-of-band connections, things like that. Access control and logging. If you have one way in and out of your environment, then you can make sure that you're using good access control, multi-factor authentication, monitoring of connections. That gives you a lot more control over what's happening in that environment. Passive network monitoring. So you can't do a lot of active scanning, but you can set up a span port or a tap and you can do some monitoring. That's awesome. That means you can also do like passive threat hunting using logs and packet captures and detection based on those types of data. So passive monitoring and detection, as old school as it is a wonderful, wonderful, powerful tool in industrial. Controlling removable media and transient assets going in and out of your industrial environments. Make sure they're scanned, restricted, checked, and that people can't plug other stuff in. You can do penetration testing and red team assessments in things like lab and digital twin environments, which means not the production system, but using the same devices. Some environments with more resourced industrial environments have these. They have a lab environment where they test updates and stuff. So it's the same devices, the same software updates, and you can bang on that and not hurt anything. So if you have that type of environment, use it for your testing. Use it for your penetration testing, your red team assessments, whatever. Or if you don't, look for those outage and maintenance windows and talk to your operators and engineers about running a test when everything's safely shut down. Make sure that you secure and monitor the higher level systems in your Purdue model when you can do that. Those are more familiar Windows systems. There might be potential when you talk to your engineers and your vendors to do things like install antivirus and EDR on those devices. If you can do it, that's great, but you can have those conversations. And collaborating with the vendor in general on enabling feasible security features. A lot of industrial control systems released recently do have some security features, but they're often turned off by default. So it takes somebody actually asking about them being turned on for them to be turned on. And finally, I'll end with some suggestions for things that can go wrong. If your OT staff hates you, they've been burned too many times, try to understand why. So be reasonable, listen to what they're upset about, and enforce that you're there to work with them, not audit them. You are not an auditor. You are not an auditor. You're a nice security dumb person there to give them donuts and listen to them. If systems are too legacy or tightly vendor controlled from modern security tools at all, look at that passive network monitoring, hunting, and segmentation. Those are your tools there. It's okay if you can't update them and they need to run Windows 95. You just need to find other workarounds. If you're having trouble securing anything, try to anything in the environment at all. Try to simply control and monitor ingress and egress. If you can control that DMZ, you can do a lot. If you can keep things from getting into the environment other than one way in and out, then you can do a lot of security and a lot of controlling of the environment. If OT people were running cybersecurity and they get upset because you're taking their work away, give them tools to participate in cybersecurity meaningfully. So let them help you build that security program. They want to do security. They think security is interesting. Don't just take that away from them. It'll spoil the relationship. Give them an opportunity to learn about what you're doing and to give suggestions about the security program you're building. And if you don't have the capacity to monitor low-level devices like PLCs or below, understand that the vast majority of attacks have to come from top down. If there's only one way into your network, then the attacks are coming from your IT environment through your DMZ into your OT environment. There is somewhere else you can do detection. It's okay if you don't have the capacity right now to do lower level device monitoring, even though that's something you should work towards. That is all I have for you. What questions do you all have? What do you want to know about industrial control system security? We've got a couple minutes before I pass it over.
If I can ask a question, how did you get into industrial control?
I've kind of been doing non-standard IT security my entire career. I worked for a manufacturing company before Dragos, and we did a lot of OT-based security and had a lot of incidents in that space. And then in the Air Force before that, I was in avionics, so I dealt with a lot of non-standard computers there. So that's kind of the space I've always been in.
Cool, thanks.
How do you find those one-off devices that don't usually show up? You can't really do a lot of active scanning in industrial environments. Usually it's a waiting game. Collect packet captures, wait for it to talk. But sometimes you can like pull switch configs, things like that, and that doesn't actually impact the network. So if you have like a Cisco switch environment in your industrial environment where you could pull, you know, some data about what's connecting to it, then you might be able to find some of those devices there. Is there anything going on with 5G at ICS? Yeah, sure. I mean, everything is getting 5G eventually. There's certainly cellular modems all over industrial environments, especially ones with distributed stuff going on in them, like windmills, like wind generation power farms, things like those. They rely heavily on cellular modems. So yeah, 5G is all over the place in industrial too. Yeah, I think that's all the questions people had. Aside from historian data, do OT systems have distinct logging? I think I understand what you're asking here. So aside from historian data is like process data. It's not security data. It's interesting to look at from a security context because it can tell you about what's happening in the environment if something's failing, but it's only operational data. Again, I think of it like SNMP. It's like, is stuff going or not going, and how well is it going? OT doesn't have like distinct security logs, really, usually. There's Windows event logs from the Windows devices, of course. Any of that normal data from Windows systems. Yeah, there's not a lot of security logging from industrial devices often, though some of the comprehensive systems for various things come with an antivirus server for the Windows systems, and that might log to you.